Hi, my name is Jorge, and I am with the Karlsruhe Institute of Technology and with the Costa Rica Institute of Technology. And for me, it's a pleasure to be part of this workshop and to present our work, AxLS, an open source framework for Netlist transformation approximate logic synthesis. I would like to start my presentation by um, introducing what is approximate computing. Approximate computing is a novel design paradigm which proposes to find a trade-off regarding the computational quality, which can be measured as the accuracy of the results, um, and the computational effort, which can be measured as the execution time, area, power, or energy of applications. This design technique has been proposed particularly for applications where there is an inherent tolerance to errors, and by allowing faulty computations or computations with a lower precision, um, savings can be obtained, and still results can be produced with enough quality, with enough accuracy for the application purposes. For instance, this is a solvable implementation that has been designed at a circuit level for different accuracy targets. And as can be seen, as the lower the accuracy target is, the lower the quality of the image, the resulting image is, in this case measured by the peak signal to noise ratio. But by allowing more errors, which in the case of these images are noticeable, lower resources are required. In this case, an evaluation of the required resources is done by the power delay product. But it's interesting to see that even in this case of this image, um, a reduction of about 30% of the required energy can be obtained, and achieving a very good enough quality. And even for the visual perspective, the errors are not such noticeable as in further cases. For the approximate computing paradigm, different techniques have been proposed, from circuit to architecture to software level. And one big area where many works have been proposed is regarding approximate logic synthesis. In a nutshell, the idea of this approximate logic synthesis is to generate approximate circuit implementations from an accurate implementation. And within this approach, different techniques have been proposed. The three main techniques can be summarized as netlist transformation, which the main idea is from a netlist that has been accurately generated, apply different techniques to reduce the gates, the required gates. By doing so, of course, introducing some level of errors, but at the same time reducing the complexity of the circuit, making it consume less power and less delay. Another technique that has been proposed in this direction is called Boolean rewriting, which aims to perform a simplification of the Boolean representation, in this case as a matrix format, before the circuit is synthesized. So by having a factorization of the original Boolean representation, and these Boolean tables generate then a simplified version of the circuit. And a third approach in this direction of generating approximate circuits, it's called approximate high-level synthesis, which keeps the main idea of high-level synthesis, which is generate an implementation, a hardware implementation for a more abstract representation of the circuit, normally from C code, but in this case introducing approximations, which, by the way, we have present in this direction a work in ICAT to generate approximate accelerators using approximate adders and multipliers from those reported in the literature, and we have integrated a specific method to do this into a high-level synthesis tool. When we wanted to work in this netlist transformation approach to generate approximate circuits, we faced a challenge. And the challenge was there was no open source framework available that we could use to first test what has been proposed in the literature by many different works, and then to propose our own approaches, our own techniques for netlist transformation. So before targeting our own ideas on how to generate approximate circuits at this level, we decide to come with an open source framework that allows anyone to test what has been proposed in the literature regarding netlist transformation for approximate logic synthesis, and of course allows us to propose our own techniques. I would like to give a description of how our tool built, and the first stage in our implementation is required in the netlist generation. We wanted to have a representation of the netlist that we want to modify in such a way that it's easy for us to manipulate the gates that compose or the circuit. For this, first we follow a very traditional approach for performing a synthesis, taking an RTL description, in our case using Verilog AxLS, and we generate a netlist for a specific technology library. In the case of netlist transformation techniques, they are tied to a specific library that is being used, but in our case, our implementation can use any technology library that can be provided. At the same time, by generating a netlist, we want to extract the netlist representation, this dictionary of netlist of gates that compose a netlist for this specific technology library. And we do this in order to generate a representation of the netlist using AXML. By using XML, it's very easy for us to manipulate the representation of the circuit and produce newer netlists from this modified representation. Additionally, the netlist can be simulated and we can get activity of the different gates, and this information is also useful to feed the netlist representation. Other information from the netlist can be also obtained and feed, for instance, like the weight that different netlists have or the impact that different parts of the netlist have into the accuracy or particular parts of the netlist, how they affect specific outputs of the netlist. Our representation of the netlist looks something like this. We use the same naming convention that the technology library is using, and we extract what is important for us, in this case the connections of the different gates to all the gates, but also to the inputs and to the outputs. So we have like here at the left, a sort of representation like this using XML, but also internally our framework is able to generate dot files, which we can use to then graphically see how the netlist looks like, and which is also useful later on to see what is the changes looks like in the netlist that has been modified. Once we have XML-based netlist representation, then we can apply the actual criteria of how to reduce the complexity of the netlist. And this is represented by these spots. What can be included in these spots will depend specifically on how you want to perform the netlist transformation. For instance, having activity information of the gates can be used as an approximation criteria to then prune those gates that have a constant value as an output, or a probability to have a constant value as an output more often. Other criteria techniques could evolve that imply that if you have a specific primary output that you want to delete, then to consider all the different nodes, all the different gates that are part of or that affect this particular primary output, and then prune all the corresponding gates. So what can be placed in this approximation criteria, it's open to the user. And in our case, and for the scope of this presentation, we have defined specific rules that we wanted to test as approximation criteria, and that I will describe later on. Whatever the approximation criteria is being applied, the idea is to then, using the XML, have an approximate version, a transformed version of the XML, the netlist that we use as an input, and we provide the functionality to convert backwards this XML representation into a Verilog netlist level representation. By doing so, we are able first to perform the simulations, which is required in any case to assess how much the pruning that we're performing, the netlist transformation we are doing, is affecting the accuracy of the results. And in any case, it's important to receive an accuracy threshold as an input to then be able to do this evaluation. How often this can be applied? This is also something there are a framework allows the user to define if every time that a particular gate or type of gate it's pruned, then to perform an evaluation, or a set of gates that are pruned, then to perform an evaluation using simulation to then estimate how much the accuracy it's being degraded. Also, with this output netlist, this approximate netlist, we can use, again, synthesis tools to obtain circuit metrics to assess, for instance, how much is the error savings that we are obtaining by performing this particular approximation criteria, or the different steps that we are applying to reduce the complexity of the circuit. These circuit metrics also can be used and can be fed into the approximation criteria to guide this pruning process, this transformation process. For the case of our current implementation of AxLS, we have been using Python language to describe all the different parts, from the conversion of the netlist to the XML, reading the XML files, generating or abstraction of what the technology library looks like, and to apply all the different pruning techniques, we have been using Python language. As depicted in the previous diagrams, we rely on external tools to perform the synthesis and the simulations. We're using currently Yosys for the circuit synthesis and Icarus Verilog for the netlist simulation, trying to maintain the entire framework as open source as possible. As depicted in one of the diagrams, it's sometimes necessary to have gate activity. Unfortunately, there is no tool available right now that it's open source that we could use to obtain values like this, but part of the following steps that we are considering as part of our implementation of AxLS is to extract the functional representation of the gates, and then be able to perform also sort of simulations internally, and by doing so being able to extract all these gate activity values that might be useful for the approximation criteria. And the evaluation that I would like to present here, we have been using some arithmetic circuits, particularly standard others, which is the case for most of the works reported in the literature that they test the approximate logic synthesis techniques on this type of circuits. And we have been using the non-gate 15 nanometer technology library. I would like to describe what are the steps that in our paper and the workshop we presented as a pruning technique, or as the approximation criteria. The first is that we want to consider primary inputs are constant, and by doing so, we consider all the dependency, all the nodes that depend on this particular input. We explore them and we test what happens if we prune these dependencies up to the primary input. Every time we do this, we evaluate what is the accuracy degradation against a particular threshold that has been provided. And if the accuracy limit is violated, then we undo the last pruning, and we continue for the following gates, the following nodes that present any dependency to this primary input. Once we explore all the potential primary inputs that we would like to explore, then we go to the primary outputs, and we consider also the primary output is constant. And in this case, we explore up to the inputs all the different gates, all the different nodes that have an effect on such outputs, and perform the same. We start by pruning those gates and exploring what is going to be the quality degradation, or in this case, the accuracy degradation of the netlist. Every time a node is removed, we replace it with a value of 0. This is an arbitrary decision, but other information can be used. In the case of gate activity, this information can be used to decide either if 1 or a 0 can be used. In our case, we decide to go for a 0 value every time a node is replaced, and this is particularly useful for other nodes that are not being replaced, but that they have a dependency on a node that is being pruned, that is being deleted. And in our case, we start from the less significant bits, in this case from the input first, up to half of the input bit width, and we do the same for the primary output, from the less significant output bit up to half of the bit width data output. This is a small representation for a 4-bit ripple carry adder, which allows to have a simple diagram to represent and to show. In this case, we can see that the different inputs, the input 0 for both inputs, bit 0, bit 1, bit 2, and bit 3, and the different gates that present dependency on these inputs and the connections between the gates. Also, we can trace the different dependencies for a particular primary output on the different gates up to the primary inputs. And even considering the carry in as one of the dependencies. If we take this netlist and we want to generate an approximate one, considering that the maximum tolerable error is going to be 8, so the maximum difference between an accurate and an approximate calculation will be 8, we can obtain by following the rules or these steps that I just described, this netlist here at the right. Here we can see that only 2 of the outputs are now available. And of course, if we go backwards, we can see all the dependencies up to just 2 of the bits of the input plus the carry in. Some of the previous wires or the previous connections that were used up to inputs that now are pruned, we can see there are still preserved to this dependency, for instance, in this node or this gate 36, which has this dependency on those previous values. But of course, by following the steps I just described, these values will correspond to 0. What is interesting here to see is, as expected in a ripple carry adder, that is that the dependency of the output 3 and 4 to the carry in is still preserved, and for that reason many gates are still present, but other of the inputs are totally pruned and no longer present in the diagram. As I mentioned before, all gates have been pruned, and the value that they were providing to other gates that are not being pruned, it's going to be a 0. So for instance, these now that they look as some inputs to a specific gates like 0, 1, 6, 5, and 9, they're going to be replaced by 0 values that are going to be fed to the other gates that remain in this approximate netlist. Internally, our tool is able to take the information from the simulations and generate an error distribution of how the approximate netlist is behaving in terms of the accuracy. This probability mass function, which is this error distribution representation here, is a very common way to represent the error distribution on approximate circuits. And in this case, this is the error distribution for this approximate netlist obtained. As I mentioned before, this netlist has been generated considering a worst case error, a maximum error of 8. And as can be seen, the maximum error which appears with a very low probability is 6, which in this case provides certain guarantee that our approximate netlist will never produce an error beyond this defined threshold. And internally, our tool can use this probability mass function, this error distribution, to obtain different of the error metric techniques that have been proposed, which allows also our tool to be dynamic or flexible in this sense, that by using this error representation, many of the common error metrics or accuracy metrics can be assessed, and we can use the different metrics proposed in the community to then generate approximate netlist. We test also our implementation of these rules into our tool, just as a matter of testing that the different functions, the different capabilities of our AxLS framework can allow an user to take our implementation and propose approximation criteria and generate approximate circuits. We tested for 3 different standard adders, Brent-Kahn adder, Kaugiston, and Karlsruhe head. For each of them, considering them for 16-bit width input data and 16-bit output. And we did a small evaluation considering 2 different accuracy metrics, the worst case error, this maximum error allowed that I just mentioned, and the mean error distance, which is a weighted average of the errors that can be obtained from this probability mass function representation, considering the error distance and the probability of the recurrence. As you can see here, we have different values for worst case error and for mean error distance, as we consider that our potential output circuit can tolerate more errors. More savings can be obtained. In this case, we consider the normalized area as an evaluation, particularly because using YOSIs, we can do these area estimations, and then we can easily integrate it to our tool to then do this assessment of how much the area is being reduced. For the case of the Brent-Kahn and Kaugiston, the behavior is very similar. In this case, and in the case for the mean error distance, for the case of the worst case error, there were some differences. When we observe, for instance, that for higher values of worst case error or mean error distance, the value or the normalized area achieved is the same. This is because at least the approximation criteria implemented cannot produce a reduced or simplified netlist beyond what has been done without violating this accuracy threshold that has been provided as a constraint for the design. In any case, our framework, it's being presented as an open source framework for this type of netlist transformation techniques. We cannot cover in our tool all the potential techniques that have been proposed, but we focus on those techniques that aim to perform a transformation on the netlist to generate an approximate one. We have made, of course, our current implementation of our framework as an open source contribution, so it can be used, it can be extended for different functionalities, but also can be used and tested for existing techniques that have been proposed. In our paper, we have shown the functionality of our framework by using or by performing some pruning techniques, these approximation criteria that I described, considering primary inputs or primary outputs at constant and performing a guided pruning for those nodes that have an impact or receive an impact from these inputs or outputs. And we tested with 3 standard adders, just as in many cases the different Netlist transformation techniques have been tested. As future work, one of the main things that we want to address is the implementation of machine learning based techniques to perform error estimation. As we are relying on simulations, this makes the exploration very slow, because every time that we consider that we need to do an accuracy evaluation to assess how much the pruning is degrading the output, we need to go for a simulation, which in many cases takes a good amount of time. So we want to implement and explore machine-based techniques to perform error estimation, and then to reduce the dependency on simulation tools. Also, as I mentioned before, we want to provide our tool with the capability to perform simulations without requiring an external tool, which also will allow us to speed up the exploration process, but also to extract gate level metrics regarding the activity of each gate, which also will help us to remain as open source as possible and not relying on proprietary applications to then get this type of information of gate activity information that normally it's being obtained just by using proprietary applications. I hope that this open source framework will be useful for people that are interested in approximate computing, but particularly in approximate logic synthesis based in Netlist transformations. Thank you very much for watching.